All right, for this problem, I'm going to work through the full percent composition analysis of this problem. And this process will be the same for any compound when you are given the molecular formula. So if you're given a molecular formula, you can break down the mass percent of each element in that molecular formula just using the formula and the periodic table. Now, when I recognize we have a problem like this, my approach is usually to kind of solve for a bunch of information right at the beginning that I know that I'm going to need for the problem itself. And the typical process for solving the percent composition is to, first of all, find the molar mass of the entire compound, because mass percent, as we saw in class, is always going to be the mass of a component over the total mass, or sometimes we say the mass of the whole. And so the mass of a component is going to be the total mass of one element in the compound. And I've actually listed those here, right? So what you'll notice here is off to the side, I've calculated what the total mass of each element is in this compound if we have 1 mole of the compound. And so I've done this by recognizing that there's 12 carbons, so 12 times the molar mass of carbon tells me how many grams of carbon I have in 1 mole of this compound. And then I do the same thing for the hydrogen. 22 hydrogens times the molar mass of hydrogen gets me the total mass of hydrogen in 1 mole of this compound. And then again, same thing for oxygen, but we have 11 oxygens. So notice when you're usually solving for molar mass, you're going to get these values and then you're going to add them all together to get your molar mass, but we don't often write down what these individual values are for each element. We usually just kind of add them up in our calculator as we go. And that's fine when you're solving for molar mass, but for a problem like this, we're actually going to need these numbers, or at least we're going to need to calculate them again if you don't write them down the first time. So I saved myself a little bit of time here by calculating all of these masses of the components, right? Because each one of those is going to be a massive component. That means that the total mass that we always divide by is always going to be the molar mass that we've got here. So in terms of how you interpret this mass percent definition based on the, chemical formula, what parts are going to be the mass of the component, what parts are going to be the total mass. The total mass is always the molar mass. The mass of the component is always the total mass of that element in 1 mole of the compound. So to calculate the mass percent of carbon, I'm going to take this total mass of carbon in 1 mole of the compound, which was 12 times 12.01, and I'm going to put that on the top, and then I'm going to put the total molar mass of the compound on the bottom, and that gets me this decimal value for the mass percent, which we'll also refer to as the mass fraction. So whether you represent it as an actual fraction or whether you represent it as the value you get from the fraction, this would be considered the mass fraction. And those values will always be less than 1 because the value on top for the component is usually less than the total mass. So we usually get a value that's less than 1 for this. But in order to express this as a percentage, we're going to basically multiply by 100% to change this into a percentage. And so that then turns this 0.42103 into 42.103% carbon. And then we're going to do the exact same thing for hydrogen and oxygen. So for hydrogen, I'm grabbing the mass of this component, which would be the total mass of hydrogen in the compound, and I'm putting that down here, and I'm dividing that by the total molar mass of the compound. So the mass of the compound if we have 1 mole of that compound. So same thing that we just did for carbon, but now we're doing it for hydrogen. And again, I get a mass fraction value when I punch this into my calculator initially, but if I multiply by 100%, I can see that that's getting me 6.479% for the hydrogen. And then I do the exact same thing for the oxygen. So again, up here, My total mass of oxygen in 1 mole of the compound was 176 grams. So I'm putting that as my mass of the component on the top. My total mass is the molar mass of 1 mole of the sucrose. When I solve that in my calculator, I get the mass fraction, and then I multiply by 100% to turn that into a percentage. And so then we get 51.417% oxygen. So next, one of the really nice things about these types of percent composition problems, where they're just asking you to figure out what the percent composition is, and let me note that, these 3 percentages we have over here that represent each element in the compound, these are what we consider the percent composition. So if you see a problem that's asking you to solve for the percent composition of a compound, it wants you to go through this process of solving the mass percent of each element in the compound and giving that, reporting that as your final answer. All 3 of these values represents the percent composition. But when we do a problem like this where we can solve for each one of these individually, a really great way to check your answers and make sure that you did the math correctly is to just add up all of these percentages and make sure that they equal 100%. Because they should, right? If each one of these percentages represents everything that's contributing mass towards the compound, then we should be able to add all these up to get 100%. And so this is a great way to double check at the end of a problem and just make sure, did you do all your calculations correctly? If you're not getting them adding up to 100%, then you want to go back and double check your calculations. Maybe you missed something somewhere. Maybe you grabbed the wrong molar mass for one of the elements. Maybe you misread the molecular formula and didn't include the correct number of elements. All of those things could be ways that you would throw off your answer and then not have them all add up to 100%. Now for the last part of this problem, we have a situation where we're now going to use the mass percent of carbon, because we're being asked about carbon here, to get the mass of carbon in a certain amount of this substance. So notice here we're told that we have 24.35 grams of sucrose, which was the whole compound. And we want to know in that 24.35 grams, how much of that mass is carbon? Well, we know the percentage of that mass that should be carbon is this 42.103%. So most of you that understand how percents work and remember your math skills with percents probably know that all we need to do is take this 24.35 grams and multiply it by the 42.103%, but in the decimal form or in the fraction form. So those of you that are really comfortable with this know that you're going to be using this 0.42103, and you would just be multiplying the 24.35 grams by that value, because that's how you take a percentage of something, right? And if you've done this with money before too, if you know that something is 60% the price, right? It's marked down to 60%, then you probably know that you multiply the price by 0.6, right? So most of you know how to do that probably. And that is definitely a valid way to solve this problem. And I think it's always asked, is it okay if we solve a problem that way? And for the most part, I'm not going to care that much. But it is also really useful to know how to solve this using mass percent as a conversion factor, because there's other times we're going to see where maybe you don't want to bother solving for the percentage. Maybe you just want to come up with a conversion factor that allows you to convert this 24.35 grams into the mass of carbon. And that can streamline certain problems and make them take a little bit less time to solve. So this is a really good technique to be aware of. And I also feel like it really demonstrates that you fully understand how mass percent works and also how to utilize mass percent as a conversion factor, which is a really useful skill to have. So all this involves is knowing that you're going to start with the 24.35 grams of sucrose, and that you're going to then set up your conversion factor utilizing either the mass percent in the decimal form like we just discussed, or you can set this up slightly differently. I'm going to give you kind of 3 different versions of this that can be set up. So this first version here is basically the same thing as just recognizing you're going to multiply the 24.35 grams by the decimal form of that percentage. So there's really not that much else going on here other than writing it out like it's a dimensional analysis. But the other way we can express the mass percent, if you know the mass percent, is to express it as 42.103 grams of carbon per 100 grams of sucrose. So notice that that's still kind of the same thing because we're still using the actual mass percent that we solved in the previous problem. So again, nothing about these two steps is really going to make this problem shorter if you haven't already solved for the mass percent, right? So what I really want to demonstrate here is that you don't actually need to solve for the mass percent in order to write the mass percent as a conversion factor, because what we can do is we can come back up here to our carbon mass percentage. When we wrote it out to calculate it, we put the 144.12 grams of carbon on top, and we put the 342.296 grams of sucrose on the bottom, right? Remember, this was the total mass of carbon in 1 mole of sucrose over the molar mass of the sucrose. If I take this expression right here, and let me duplicate it and bring it down, this is basically going to be what we can use instead of the calculated percent, right? And so note why am I bothering to show you guys this? Why did I stress this so much in class that, you can do this? Well, first of all, you're going to see me doing it a lot more in the next few problems on this worksheet. But second of all, just note here again that if this problem, if all it asked was, hey, here's the molecular formula of sucrose, and tell me how much mass of carbon is in 24.35 grams of sucrose, this would be the only calculation you would need to do to solve for this answer of 10.25 grams. You wouldn't have to solve for the mass percent in the middle, as a initial step, because you're just setting up the mass percent as a conversion factor, and it still gives you the same answer. And notice how the units are still the same here too, right? Our grams of sucrose is canceling out in each one of these, even though we have, totally different numbers essentially on top and bottom of these conversion factors. It's still working the same way. So it's just representing another way to kind of represent the mass percent as a conversion factor. And so again, this method right here, we're going to see this a bunch with the next few problems. I'm going to use this method a lot, and it's just another way of kind of taking out a step, right? Making this go a little faster so that when you're asked a problem like this, you don't have to calculate the mass percent first. You can just calculate it as part of the calculation of this answer. Obviously, if you were given a problem like this one where you're calculating all the mass percents first and then you're going on to calculate the final answer, that's fine. If you just want to use these top two methods, heck, it wouldn't even matter if you ended up giving it as, 24.35 grams times 0.42103, and that's it. If you just show it to me like it's a percent calculation, that's fine in this case. But I am going to be looking for this method for the next few types of problems, because that is something you should be using for other problems that are a little bit more complicated, where we're not going to need to calculate the mass percents specifically.